Hello, everyone. We're going to talk about vectors today, which is a very, very important thing in physics. I know that you probably have had some experience with it in mathematical terms. In physics, this is essential. It's essential to understand what they are. It's essential to understand how to use them and how we can visually and graphically see it, and how we turn that into a written mathematical explanation of them. So to start, we're going to start with just what a vector is. And I have my grid on here, so that hopefully this makes it a little bit easier. But I'm going to draw here a vector. And this vector I'm going to label as a vector A. And as a vector, we put a little vector symbol over that. So this vector here, this vector A, has a certain magnitude or a certain size, which is the length of the vector. And we write that magnitude as something like this. Right? So you may be used to those being absolute value signs, but for a vector, those vertical lines tell us that we want the magnitude, or it's the size of this vector. Another way we write it is simply as the vector name itself, without an arrow over the top. Sometimes in textbooks, the vector is bolded, and then the magnitude of the vector is not bolded. But we can write it in any of these ways. Okay, and so making sure that we understand the difference and recognize and visually see the difference is very important. This is a vector, the one with the arrow, and these are not vectors. These are a magnitude. This is a value, right? So if, say, this vector had a size of 2 meters, right? If it was like a position vector, then this magnitude would be 2 meters, right? But the important difference between this magnitude and a vector is that this arrow, right, this vector, has a direction in which it is pointing. It has a start and it has a stop, and it's pointed in that direction. And so the importance of a vector is that it has a magnitude and a direction. That's supposed to be a plus sign, meaning and. I guess I could just write it out, right? So the I guess adding has a different connotation here, so we'll just write it out as and, right? So so let's see. Let's draw another vector. Let's draw a vector that looks like this. Okay, this vector is different than this other vector, so I'm going to label it as a B vector. But why is it different? Right? It's different because it's, one, pointed in a different direction, and so therefore it cannot be the same vector as vector A, because A is pointed in one direction and B is pointed in a different direction, and so therefore it is a different vector. It could also vary in size. I think these ones actually, did I make them the same size? 1, 2, 3, 4, 5 over, and 1, 2, 3, 4 up. 2, 3, 4. Nope, it's a little bit different size. Okay, so it could also vary in size, right? So we could have, let's see, can I do this pointed in the same direction, but a different size? I don't know if I can because it's locking right now. I'd have to make a bigger one. But, well, I guess I could do that. 1, 2, 3, 4, 5, and 1, 2, 3, 4 up. So let's go 1, 2, oh. You actually have a vector here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So this vector is pointed in the same direction as A, but it's a different size. So let's actually call this one, C for right now. Okay, so C is in the same direction as A, but it is larger than A. Specifically, it is 2 times the size of A. So I could write this vector as C or as 2 times A. Now notice, right? This 2 times is saying that it is twice the size of this original A, and it doesn't mess with the direction, right? So if we write something like this, this tells us that whatever vector is on the right side has to be in the same direction as whatever is on the left. Okay, so this tells us that the C vector is in the same direction as A, but that its size is just twice as big. Okay, so an important part of when we start to write things like this C equals 2A, is that whatever, because vectors have magnitude and direction, whatever direction is on the right side has to be the same direction as on the left, or vice versa. Whatever direction's on the left side has to be the same as the direction on the right. And technically the magnitude as well. But the importance is that we can play with that magnitude a bit. So let's see what we want to do now. So one thing we can then do is we can move this vector around, and no matter where it is, it will always be the same vector. So let's see if it lets me do this. If I take vector B, and I copy it, and I paste it, oops. All right, we'll take this vector here, and I move it around. If it's there, or if it's here, or if it's here, or if it's, or wherever it is, right? I could take this vector and I could move it to the moon. It doesn't matter where it is, as long as it's this size and in this direction, it will always be vector B. Always, as I've labeled it, and as we've shown it here, okay? If it changes direction, then it's not vector B anymore. If it changes magnitude, it's not vector B anymore, right? It's something different. So that's one of the cool things about vectors, is we can move it around wherever we want them to go, or wherever we want them to be. But if they are the same magnitude and they're pointed in the same direction, they will always be that vector. So we can do something like this. We could take vector A, 1, 2, 3, 4, 5, 2, 3, 4. So here's vector A, and I've now put it, I've moved it, right? I've just moved my vector A. I haven't done anything else with it. I've moved my vector A, I put it over here, and it's touching the tail of vector B. Now, what I am doing here is I'm doing something called adding. I am adding vectors. And when we add vectors visually, this is how we do it. We put one at the end of the other, and then put the other one from the end of the, wow, I said that very weird. We put one of them and have it touch the end of the other, and that is how we get, that's how we add them together. But then the resulting vector is one that goes from the base of the first to the end of the second. So this vector here is our resulting vector. We'll call this vector R. But visually, this is how we do this. But again, we can add them together in any way we want, as long as they touch from the bottom, from the end of one to the end of the other, right? So we could also do this as B plus A, or vector B plus vector A, right? So that means that we start at B, and then we add a vector A to the end of vector B, which goes 1, 2, 3, 4 over, 1, 2, 3, 4, 5 up, or is it 5? It's 5 over and 4 up. 2, 3, 4, 5, 1, 2, 3, 4. So there's my vector A. I've added that to the end of vector B, and my resulting vector starts from the, or goes from the start of B over, whoa, that's not what I wanted to have happen. I wanted this. There we go. And that is my resulting vector in this case. Notice, when we add vectors together, no matter the order, it comes out to be the same. Haha, right? So this is an important tool in when we are dealing with lots of vectors and acting on things. So vectors, again, is a magnitude and direction. So we'll see this with velocity, we'll see this with acceleration, we'll see this with forces, right? We'll see this if we have like a tug of war, right? Tug of war, we have forces on either side of this rope and this rope is being pulled. We can discuss the forces in terms of vectors because they have a magnitude and direction in which that rope is being pulled, right? Being pulled apart. And we can analyze and see if that rope is moving at all, because that's what tug of war is. And so we'll be able to manipulate these vectors and describe how they relate to each other graphically like this, or in terms of mathematically. So we're going to have this new idea, or if it's not new, then you've probably seen it somewhere in like a math class. And we'll call it vector notation. And what this allows us to do is write a vector in terms of really we can write it in terms of orthogonal pairs, right? So two directions that are orthogonal. And what does orthogonal mean? Orthogonal means that it's perpendicular. So over here, orthogonal means that it is perpendicular, and that's how we write perpendicular. So in physics, we do this a lot, and so hopefully start to get in a sense of this concept and idea of we like to do things as simple as possible, right? Physics is complicated. The world around us is complicated. But if we can simplify things, then we can get a better understanding of how things are working. So in terms of these vectors that I've drawn here, A, B, and even C, right? If we can make a mathematical description of it that is very simple, then I can use it in lots of different ways, and I can use it simply. So for convenience, we want to choose two vectors that we can add together to give us our resulting vector. Specifically, let's look at vector A again. So our vector A, and you've probably caught on that I'm doing this in terms of vector A as being 1, 2, 3, 4 across, and 5 across and 4 up. 3, 4 from its point. And so if we take this vector to be our resulting vector, and we'll call this resulting vector A. I want this to be in this particular color, so give me a second here while I do that. Let's make it red. Make it red. Make it blue. Sorry, kid shows. So now, if I have this as my resulting vector, and I say I want to make this resulting vector, right? So notice we have resulting vectors here, and I want to add two vectors together in order to get this vector, I'm going to choose two of them that are orthogonal to each other. So I'm going to choose one that goes this direction, and I'm going to choose another one that goes in this direction. Okay, so again, when I say orthogonal, I mean that they are perpendicular. So these two vectors are perpendicular to each other. And so let's call it, I'm going to call this one X, and I'm going to call this one Y. So if I add these two vectors together, my resulting vector is vector A. So notice we did this the exact same way that we did it up here. We took X, we started at X, we added here, and then we put Y from the tail of one, or tail of X, and brought it up top, and our resulting vector connected the start of one to the end of the other. And so we have a sum of these two vectors, and we've added them together, and they've given us a resulting vector. We can do the same thing for B. How big is B again? 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Oh, it's a 4, 4. Okay. Well, that's easy. So 1, 2, 3, 4. 1, 2, 3, 4. All right, that's my vector B. Oop, I want this to be my resulting vector. So while I'm going through this, can you make convenient vectors to add together to get this resulting vector B? Here I'm going to call it something slightly different. I'm going to go this way, 4, and I'm going to go this way, right? So adding these two vectors together gives me vector B. They are perpendicular, and that is only for convenience. Okay, I'm going to call this one, let's see, what do I want to call it? We'll call it B sub x. Oh, I want to be careful with that because sometimes that's, I'm just going to call it some other letters here. We'll call it beta, and we'll call it gamma. This is something also that you'll see in physics a lot, is that we use Greek letters. All that it is just another letter to us. All right, these are just letters. So if we write this, we have vector beta added to vector gamma is going to give us a resulting vector B. Okay. Now, the importance of them being orthogonal, and the reason why that's convenient is because we can now describe these vectors in terms of a direction. So if I have a direction that looks like this, or I guess a coordinate system that looks like this. What happened? I don't know what happened to that, so I'm going to have to do it freehand. Okay, generally, we have a coordinate system that looks like this, where this is positive y and this is positive x. Generally, that's the case, and this is kind of what we're used to. And so we can write each of these pieces of B and pieces of A in terms of the x and y directions, because this is something that is 90 degrees, right? These two coordinates. And so if I take my, let's start with our x, well, let's start with our beta. We take our beta and we take our gamma. Well, and that's only 3. 1, 2, 3, 4. 1, 2, 3, 4. So here's my beta, and here's my gamma. Then I have my resulting vector B, which looks like this. Notice then that these vectors, beta and gamma, are along the x and y coordinate system. So that means that we can now describe these pieces of the vector along a coordinate system. Specifically, if this vector beta has a magnitude of beta, notice no vector notation, and it's along the x direction, then we can write it as the following. I'm going to put it over here. So our beta vector is made up of some magnitude of that vector, which is beta, along a direction of I hat. And I'll talk about what that I hat is in just a second. For gamma, we can write it as gamma j hat, meaning that this vector has a magnitude of gamma, whatever size that is, and it's in a direction of j hat. Now, this I hat, j hat, and the third direction of k hat, which is what we use along the z, these are defined as unit vectors. And a unit vector is defined as having a magnitude of 1. So each of these vectors has a magnitude of 1. And these vectors have this hat, and that hat denotes it as a unit vector. It's a special vector that has a magnitude of 1. Okay, so it has a magnitude of 1, but the direction that each of these have is specific. It has this I hat is a direction along the x-axis. The j hat is a direction along the y direction. So this has this gamma, for instance, has a magnitude of gamma along the y direction. And instead of having to write along the y direction every time, we simply state that it is gamma times this j hat. And that's all that unit vectors are. Unit vectors is a vector of magnitude 1 that is pointed along one of those axes. All right? So specifically, I guess we could draw it like this. All right? So if each of these has a magnitude of 1, then this is the j hat vector, and this is the I hat vector. Because again, when you multiply something by 1, it's just itself. But in vectors terms, then it gives it a direction. So here, where we've written out our beta and our gamma, it has a length of beta, whatever this beta vector, but then we multiply it by the unit vector, which has a size of 1, so it doesn't change the size. But what does it do? It gives that beta a specific direction, and specifically, it gives it a direction along the x-axis. For our gamma here, the j hat gives whatever vector size, that magnitude, it gives it a direction along the y. Now, one last thing. There's something special, or something not necessarily special, but something different about the j hat, right? On my axes here, I put positive y up and positive x to the right. But gamma is pointed where? Gamma is pointed down. So this actually has a value of negative. It's pointed in the negative direction. All right, sorry, let me write it like this. Is equal to gamma negative j hat, which just means that we're flipping that j hat to be in the negative direction. So this is a negative j hat. So this is how we define vectors. We define them by these unit vectors because that gives us a direction specifically to our coordinate system. So that means that we can now write our resulting vectors in terms of unit vectors. So specifically, if we replace each of these pieces with the vector that we wrote over there, then we have beta along the I hat direction and gamma along the negative j hat direction. Or in other words, our B vector can be written as beta I hat minus gamma j hat. And that is vector notation. It tells us specifically the magnitude of the vector, of one of the vectors along an axis, added to another vector in a different direction. And the result of that is our final vector. So vectors are very important, and they allow us to combine these vectors in different directions, all based on some axis. So I'm going to do one more thing. I'm going to pull this down here. And what I'm going to do is, instead of using this vector notation here, I'm going to take this. So here's our vector B again. I'm going to take this vector B, and instead of using our axes that we are kind of normally used to with our x and y, I'm going to take that axis and I'm going to rotate it. I'm going to take that axis and I'm going to say, I want an axis to look like this, where this direction is my positive y, and this, is my positive x. Okay, so all that I've done is I've taken our axes that we're used to going straight up and down, and I'm tilting it. I'm tilting it sideways and aligning it with B. And that is perfectly valid. That's one cool thing about our axes, is that all that we've said for our axes is that they must be orthogonal, right? And we have a z vector that we also have that's coming out. But the z vector, the y vector, and the x vector are all perpendicular, and no matter the direction or position, because they're just vectors, where we put that, it will always be the same with how we've defined it. So in this case, I've now defined my x and y axes as tilted. That's perfectly okay. So if I have, if I want to now make up my vector b in terms of two vectors to give me a resulting vector, right? So if I have my resulting vector b, and it's going to be made up of two vectors, the two vectors that I want it to be in is I want one in the I hat, or the x direction, and I want one in the j hat. Okay, so with this configuration, let's first start with the y. How much of vector b is in the y direction? The answer to that is there's none. There is no part of b that is in the y direction. And so by tilting our axes, what we've done is we've put all of b in the I hat direction. And so it's just whatever the magnitude of b is. Whoa, where's my cursor? There it is. The magnitude of vector b is in the I hat direction. And so this allows us even to make it even more simple to describe these vectors, is if we do a rotation of our axes. And we will do that a lot in physics. We'll do a lot because, again, we're looking for simple ways to describe how things are acting in the world around us. And in order to do that, we do things to make our lives simpler. One of them is using unit vectors. If we use unit vectors, that allows us to rotate our axes to make it even more simple for us. And so this is one way and one tool that we'll be able to do that. So make sure that you get practice with unit vectors. Make sure you get practice on how to add vectors together. Make sure you get practice on how to divide them up into these different components. So that's the last piece that I'm going to talk about, is how we divide them up. So I'm going to go back and use my vector A as our resulting vector here. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so this is our vector A. And I'm going to use, we're going to set up our axes. Oh, I guess I'll just set them up here. I'm going to do them dash though, because I'm going to draw the other vectors here. So this is our positive y direction. This is our positive x direction. And so now, again, we want our resultant vector A to be made up of two vectors. And specifically, we want those two vectors, for convenience, to be along the I hat direction and one along the j hat direction. Okay, and the way that we then do that is we draw a vector along x until it reaches the x size, and we draw one along the y. And these I'm specifically going to call a sub x and a sub y. So this tells us that the magnitude of a, or the a vector, has a vector. Wow. The resulting vector A can be made up of two vectors, one along the I hat direction and one along the j hat direction. So when we add them together, we have an x piece of A along the I hat and a y piece of A along the j hat. Oh, sorry, that's too big. That should be smaller. So this is a y sub A and an a sub x and an a sub y. And by adding those together, we get our resulting vector A. The next piece is, what's the direction of A and how can we get that from here? Well, this angle, referencing from one of the axes, right? We could go this one or we could go this one. We'll call this one phi. So theta or phi, we can get based on this using trig, specifically SOHCAHTOA. If you're not familiar with that, then brush up on your trig a little bit. Okay, what this allows us to do is look at this angle, either theta or phi, and say, we can get these angles based on these sides of vectors because look, this is a right triangle. And so we can get those angles from that. So let's do an example. Let's do the sine of angle phi is equal to what? SOHCAHTOA tells us that it's the opposite over the hypotenuse. So the opposite from phi is a sub x. So that is the size of that triangle, of the length of that side, divided by its hypotenuse, which is the magnitude of a, or just a itself. Okay? Then to get that angle, then we do the inverse sine of that, of the ratio of the magnitudes, and we get the angle of the vector based up here. Okay? So again, the importance of this is that we're going to be able to write vectors in terms of the sum of vectors. And that is vector notation. Vector notation takes a vector and it breaks it up into components, breaks it up into its unit vectors. And unit vectors are very nice and convenient because we can take the magnitude of whatever size that is and multiply it by these directional vectors, which are the unit vectors. Along with that, we can rotate our axes so that the I hat and j hats are aligned at different angles in order to make it convenient for us, right? So I know I keep saying last thing, but this is my last thing. So if we took our A vector and we aligned the axes with it, because we just did this with B, so I'm now doing it with A, and this was our positive Y, and this is our positive X. How could we write the vector notation of A in this configuration? Specifically, it would be, right? Well, let's do this. Sorry, I'm getting ahead of myself. Right? So we have, let's do I hat and a j hat. So in this case, how much I hat do we have? Well, none. There is no part of A that is along the x direction. So the magnitude of this part of the vector is 0, which means that all of it is in the y direction. So again, this simplifies things a lot because we can write it as just a one-directional vector because we've rotated our axes. Now we might have to take into account that rotation, which you'll see a little bit later on as we go through lots of other these physics terms, specifically when we start doing inclined planes and things. But make sure that you get practice with these vectors because we are going to use them over and over and over again. Great. Thanks for watching.